A warm welcome to this lecture. We saw yesterday how the Fourier transform comes about as a requirement for identifying the way a system behaves in terms of magnitude change and phase change that a sine wave has. And today we are now going to look at properties of the Fourier transform. So we are going to first build. Yesterday we actually just built the idea of a discrete time Fourier transform. And today we are slowly going to graduate to the continuous time Fourier transform, followed by the properties of the Fourier transform, and then we are going to interpret those properties. Each of those properties has an interpretation. That's the purpose of the first part of our lecture. Later on, depending on the time that we have, we shall generalize. The Fourier transform is a tool that can be used in some situations, but not in all. And therefore, to make the context of application broader, one needs to generalize the Laplace transform. We will try and see if we can also talk about the Laplace transform and how it generalizes from the Fourier transform. And correspondingly, we will also talk about the Z transform, how it generalizes from the discrete time Fourier. Right? We must see them all as moving from one to the other. That is how we should see them. Now, we saw yesterday that the discrete time Fourier transform can be described as follows. I'll write it down. By the way, there is a good reason why we are in this course, we are using the Blackboard chalk and talk method, as they say. There is a good reason for it. Whatever be the views of modern educationists, I still believe that unless you work with the instructor, you don't learn as much as you would in a classroom, right? So, working with the instructor is absolutely essential. That means, even if, now for example, I have taught this subject more than 10 times, I'm sure, 10 I'm saying, at least more than 10 times. But I still want to write down those things on the board, because I want you to write with me. And even if you think that, you can, so, theoretically everything is available in a book, but that doesn't mean it's there in your mind. What we want is it should be in your mind. And for that, you have to write it. And I'm not saying simply copy it from the board, you must also reflect on what you're writing. That's the reason why in a course like this is supposed to be a teacher's enrichment workshop where you want to enrich your mind. So you don't want to simply give you books, right? It's the mind that must be enriched. The discrete time Fourier transform, or the DTFT as we call it, is meaningful for any sequence. Any sequence in principle could have a DTFT if that quantity converges. So yesterday we defined this. We now define the discrete time Fourier transform of a sequence. We define it as capital X e raised to the power j omega. So it's a function of omega really, but we write it explicitly as a function of e raised to the power j omega. There's a reason for it. Later we'll see this also helps us generalize the idea. X of e raised to the power j omega is summation over all n xn e raised to the power minus j omega n. And we saw a particular example of this yesterday, when we took the impulse response and took the inner product of the impulse response with a rotating complex number. In fact, this can be seen to be the inner product of x of n, the sequence xn, with the sequence e raised to the power j omega n. So, in fact, the discrete time Fourier transform at some level is really an inner product. It's a kind of projection. It's very important that we interpret. You see, when you think of signal processing in terms of linear algebra principles, there are beautiful interpretations that emerge. We shall see them as we go along. This is the first one. The discrete time Fourier transform is an inner product. Now, strictly speaking, when we say inner product, we must also specify the space in which we are talking. So, what space does this sequence fit? Can you take any sequence? For example, could you take the sequence xn equal to 1 for all n greater than equal to 0. Is this admissible for calculating a Fourier transform? But it turns out strictly the answer is no. So if you were to take this quantity for the sequence xn, which is 1 for all non-negative n, strictly speaking it would not converge. In fact, much worse, if you were to take xn equal to say 2 raised to the power of n, this is definitely not admissible. So the discrete time Fourier transform of this sequence does not exist. It doesn't converge. That quantity will not converge. You can see, in fact, the reason why we are starting with the discrete sequence instead of taking a continuous time function is that it's easier to understand the discrete context first and then move to the continuous. So here you can see very easily. In fact, you can see that the discrete time Fourier transform of this sequence, if it all exists, should be of the form summation n going from 0 to infinity 2 raised to the n e raised to the power minus j omega n. Now this can be seen to be a geometric progression with a common ratio of e 2 e raised to the power minus j omega, which has a magnitude greater than 1. So obviously this will definitely not converge. So in that sense, the discrete time Fourier transform is not a universal truth. That means that we must talk about the convergence of the discrete time Fourier. One sure shot case where the discrete time Fourier transform converges is where this common ratio is less than 1 in magnitude. So let's take another example. If you took the example xn is half raised to the power of n. Now I'm introducing a notation un. Un is a sequence, it's called the unit step sequence, and it is 1 for all n greater than equal to 0 and 0 else. So let's do this exercise. Let us calculate the discrete time Fourier transform of this sequence. Now again here I would like you to do it individually first. Take 2 minutes to do it individually, 2 to 3 minutes, and then you can discuss it with your partner and improve your result if you do discussion. So in all, we should, at the end of 4 minutes, we have a few volunteers to tell me the answer. So please calculate the discrete time Fourier transform. Yes, do we have any volunteers ready with an answer? Oh, very good. You're also ready with an answer. Anybody else is ready with an answer? Yeah, you're also ready with an answer. So maybe we'll invite you this time. Yeah. Bring your notebook along to us. No, we'll invite Professor Patel. Yes, that's correct.
This is a geometric series. The common ratio is less than 1.
Yes, in magnitude.
So we can write it as 1 upon 1 minus common ratio.
The expression there needs correction, isn't it? Is there a correction required here? Yeah, there's here. That. That is. That's good enough. I think that's correct. Yeah, that's correct. Thank you so much. That is correct. Yes. Thank you. So as he says, the discrete time Fourier transform of the sequence is 1 by 1 minus half e raised to the power minus j omega. So you see the discrete time Fourier transform of this exists. Right? It's easy to calculate also. There are of course several sequences for which the discrete time Fourier transform exists. There are several for which it doesn't exist. But what we shall now do is focus our attention on those sequences for which it exists. And in fact, now let's take the more general situation. What role does the discrete time Fourier transform play? Let's go back to the system that we saw yesterday, and we'll generalize that system. So suppose you had a system like you saw yesterday, where you related xn and yn. Now, what is the more general form of that system which you saw yesterday? Let's put that down. You see, in general, the system that you saw yesterday was like this, something like y of n. So we had two or three systems. You saw xn plus xn minus 1, then you saw another one where xn minus 1 was calculated. And in general, you have a system, one class of systems called linear shift invariant system, but I don't want to use that terminology here. I'm just saying a general class of systems which is very useful in discrete system theory is the one where y of n is a linear combination of the x of n. And in fact, again, if we want, we can confine ourselves to that situation where in calculating y of n, you only involve x of n and the past samples of x n. So there is a certain, causality in the system. The cause-effect relationship is away. Otherwise, in principle, the most general class is y of n is summation k going from minus infinity to plus infinity, h of k, x of n minus k. That's the most general class. So essentially, you have a linear, each point on the output sample, or each point on the output sequence is a linear combination of all the input samples in principle. That is a fairly general class, which is very useful. And in fact, it turns out then that the impulse response of this, so if you were to give an impulse as the input to this system, the response that you would get is indeed this h of n, right? The impulse response of this, what we saw yesterday, the impulse response of this system turns out to be h of n, the sequence h of n. So therefore, one general class of systems that is very useful in discrete system theory is where you use the impulse response samples to make a linear combination of the input samples in the way that has been shown. In fact, if you look at yesterday's example, you remember that h of n yesterday was half. This was there were two finite length sequences, half and half minus half. And now you will recognize, if you use this expression, you will recognize that you will get back these two systems that you saw yesterday. Isn't it? If you use this definition here, you would have h of 0, that's half times x of n, plus h of 1, that's again half times x of n minus 1. And in this system, it would be half times x of n minus half times x of n minus 1. So you see the correspondence with what we studied yesterday. It's a more general form of that system. In fact, these systems, we now give them a name. This class of systems is called the class of linear shift invariant systems. And there are some very powerful properties which the discrete time Fourier transform has as far as the behavior of linear shift invariant systems is concerned. Why are they called linear shift invariant systems? In fact, I am going to now state two results, and then they are not directly relevant to our discussion, so you won't spend time proving them, but then you could prove them on your own later. These systems are called linear shift invariant systems because they obey the following two properties: linearity By linearity we mean the following. If you gave two inputs, if you performed 3 experiments on the system, the first experiment is give it some input x1 of n and observe the output y1 of n. The second experiment, you give it some other input. It could be the same or it could be another. x2 of n and observe the corresponding output y2 of n. And in the third experiment, you make any linear combination of these. Pardon me? Yes, yes. No. So when you see here, now this is a discrete time system, so it's a mapping from sequence to sequence, not point to point. Again, let's remember, a discrete system is not a mapping, if it's a mapping from point to point, it's a very restricted class of discrete system. It becomes what is called a memoryless system, but we are not interested only in memoryless systems. The most general discrete linear shift invariant system would map the sequence to the sequence, not point to point. Okay? So that in the third experiment, if I took any linear combination alpha x1n plus beta x2n, then the output must also be alpha y1n, the same linear combination. And this must hold for all x1, x2, alpha and beta. This must hold for all x1, x2, alpha and beta. If that is true, we say the system is linear. So, you see, any property, when you say property, a property really is a prescribed outcome of prescribed experiment. What is a property? A property is a prescribed outcome of prescribed experiment. So, here the prescribed experiment is take two sequences, find out what the system would produce when that sequence is applied as the input, take a linear combination of those sequences and see what the system produces. If the system produces the same linear combination of the corresponding output, we say the system is linear, provided this happens for all such input pairs and for all such linear combinations. The other property is shift invariance. I'll write it right here. Now, shift invariance again, what is the prescribed experiment? The prescribed experiment is take an xn and find out the corresponding output. Now, shift the input. So, apply x of n minus d, where d is any integer, and query what the output is. If the output is also y of n minus d, and this holds for all x and for all d, we say the system is shift invariant. What does it mean? It means if I shifted the input by d sample, d can be positive or negative, then the output suffers no change except that it is shifted by the same d sample. That's called shift invariant. Well, what is the physical interpretation of shift invariance? It really means constancy in behavior of the system. So, it says that, if the system behaves like this today, it will also behave like this tomorrow. That's what shift invariance is. Constancy in behavior of the system. If you went to the laboratory and performed an experiment with some setup there, and if you went tomorrow to the laboratory and performed the same experiment, you should see the same consequence. That is shift invariance, right, in a certain sense. The time behavior is just shifted by the point of performance of the experiment. Now, this expression that we have, y of n is summation k equal to minus infinity plus infinity k xn minus k, is the most general description for a linear shift invariant discrete system. That's the most general description. What it means is, the impulse response tells you everything that you want to know about a discrete linear shift invariant. If you know the impulse response, you know the response to a unit impulse, you know how that system responds to any input. So, therefore, in particular, you know how that system would respond to a rotating complex number, and how it responds to a rotating complex number is now what we are going to study. So, let us apply a rotating complex number in this system. However, we would like first to, so let's look at this expression. Let's give the input xn equal to e raised to the power j omega. We have this system y of n is summation k going from the linear shift invariant system in general and to it will give the input x of n is e raised to the power j omega. It's a rotating complex number. Remember why we talked about the rotating complex number. Two rotating complex numbers come together to make a sign. Now again, I give you 2 minutes, 2 to 3 minutes, obtain the output for this input and write it in the following form. Can you write it as a multiple of e raised to the power? So can you show that the output is a multiple of the input here? And what is that multiplying factor related to the, so this is the question. Fine. Show that it is of this form and obtain this, what comes in the bracket there. So again, let's take 2 to 3 minutes to do it ourselves first, individually, and then you may consult your partner for 1 minute or so and see if you can improve your answer. Oh, some people say they're not clear. You need to find out the output for that input, e raised to the power j omega n, for any constant, particular constant omega, and show that it has that form, some multiple of e raised to the power j omega, and find out the multiplying factor as a function of omega. No, hk would be given to you. So hk would be, hk is a part of the system specification, like we did yesterday. Right? So hk is known to you from the system specification. So you can assume that hk is known to you. Hk as a function of k is known to you. For example, you had 2 examples of hk yesterday. Do we have a few volunteers ready with an answer? You're ready with an answer? Yes. Do we have? Good. So I think we are nearing. So how many volunteers do we have for an answer this time? Oh, you are ready. You are ready. You're also ready. Who else volunteers this time? You're ready. Okay, I think this time we'll invite you. You can bring your notebook along tonight. That is, yeah, very correct. Yes, I think he's perfectly correct. How many of you get this? Raise your hand. Oh, that's very good indeed. Yes. How many of you don't follow some step here? How many of you doesn't follow a step here? Very good. So now, in fact, if you think about it, it's a very beautiful interpretation that we have here. When you gave e raised to the power j omega n as the input to the system, what you get is e raised to the power j omega n multiplied by a constant which is a function of omega, of course. However, that constant needs to converge. This is an infinite summation k going from minus to plus infinity, hk into e raised to the power minus k omega t. Can we interpret this? Of course, what is this quantity? It is the discrete time Fourier transform. So what is, now this is h of e raised to the power j omega. Is that right? So it's essentially the discrete time Fourier transform to impulse response. So you see, we have a very beautiful and simple interpretation. What is the linear algebraic interpretation of the discrete time Fourier transform? It's an inner product. The inner product of the impulse response with e raised to the power j omega n. What is the physical interpretation of inner product? What does it give you? It gives you a projection. So it tells you what component of the impulse response, so to speak, lies along e raised to the power j omega. This makes a lot of sense. It says that if I gave e raised to the power j omega n as an input to this system, the output is e raised to the power j omega n multiplied by the component of the impulse response along e raised to the power j omega n, so to speak, informally. One can't really say this very formally, but informally that's what you're saying. That when e raised to the power j omega n is given as an input to the discrete time linear shift invariant system, then the output is e raised to the power, the same e raised to the power j omega n multiplied by the component of the impulse response along e raised to the power j omega n. Now, this doesn't happen for all sequences. In general, if you took any sequence xn, the output is not going to be a multiple of x. That is true only for some very special sequences like this one. And these sequences are called eigensequences. You've heard the term eigen before. Verma, eigen, does it in German, does it mean one's own? I was just trying to recall. I think, yes, somebody knows German here. I mean, I'm told that eigen in German means one's own. You know German? No, you don't know German. Who knows German here? Trying to. So I heard, it's interesting. Even if it doesn't mean, I think it's still, give it that interpretation. Eigen, I'm told in German means one's own. Eigen vector, eigen sequence, eigen really means one's own. So the system's own sequence. And in a lighter vein, how do you treat your own people? When you go back home, you normally come back multiplied by a constant, isn't it? That's what happens to an eigen sequence too. When it goes into the system, it's the system's own sequence. So of course, treated very well when it goes into the system, comes back multiplied by a constant, well fed and nourished. Yeah? So the word eigen is used in eigen could be used in the context of vector, sequence, value. Okay. So in fact here we say this is an eigen sequence and this is the eigen value corresponding to the eigen sequence. Of course, this particular eigen sequence is really a rotating complex number. And in fact, this is not, it's not very different from what you studied in matrix. In fact, if you think about it, you could think of the system as an operator. In general, this is like an operator. You'll understand that even better if you took a finite length impulse response. For example, if you were to take the two systems that you saw yesterday. See, you saw two systems yesterday. So let's take the example of half-half. Now, suppose you took an input sequence and restricted yourself to some part of the input sequence. So let's say the input sequence itself is restricted in length, right? So you have xn is of the form, say x0, x1, x2, x3, only 4 samples, right? Then you would get a corresponding yn. How long would yn be? Well, yn would not begin before this, but yn would go all the way up to y4. So, of course, you can always append a 0 here, there is no problem. And now, if you take this restricted version of the system, where you treat this as a 5-dimensional vector, so you treat this as a vector y, and you treat this as a vector x, then you can write the vector y as some matrix A times the vector x. And now my exercise for you is please obtain the matrix A. Let's take 2 minutes again and obtain the matrix A. And then of course you can obtain it yourself and then consult your neighbor and improve your answer. You must write the vector y as a matrix times the vector x. What is that matrix A, which multiplies x to get y? I recommend that you write down, it's never, that's why, we do it. You can write down the expression for y0, y1, y, that will make it very easy to you. And then see the connection with that impulse response. Do it for the specific case, not in general. For the specific case of half your impulse. You can already see a few correct answers here. Yes, so are we converging to an answer? How many, we have some volunteers for an answer? No volunteers so far? You have that, we have one volunteer. Any other volunteer for an answer? Alright, I think I'll invite him again. So, I must invite Dr. Mukesh Gupta again. Yes, you can erase this one. Yeah, erase the mic.
First we have to write the equation of the system, and for various values of n, starting value of y of 0 is equals to 1 by 2 x of 0 plus x of minus 1. For n equals to 1, y of 1 equals to 1 by 2 x of 1 plus x of 0,
And so on.
and so on. So we write this in the form of vector matrices. This is y0, y1, y2, y3, y4. This is equals to, so we have to get y0 when we are multiplying this matrix to a vector x, x0, x1, x2, x3, x0. So we have a coefficient 1 by 2 and corresponding to x equals to 0. So this will be the 1 by 2 and rest all other. To get y1, we have 1 value, 1 by 2 values corresponding to x1 and x0. So first two values are 1 by 2.
That is.
Simply shifting these two.
That is very correct.
Completely.
This is 5 of 10. Yeah, you should involve. Yeah, that's correct. That's okay. That's fine. Because anyway, you have a 0 in there. Very good. That's correct. How many of you get this? Very nice. How many of you don't get it in the sense that but you know how to do it now? Anybody who doesn't know how to do it now, everybody knows how to do it. So what does it tell you? It tells you that if you were to take the, so you see, it tells you that the eigenvalues of this matrix have something to do with that discrete time Fourier transform, the impulse response. In fact, now we come to a more general result. So this is, so the reason why I mentioned this is that when we use the term eigensequence, it's a generalization of the idea of an eigenvector. The eigenvector of an object. So here we are talking about this eigensequence being a special kind of sequence for that operator which the system represents. The behavior of that operator is completely characterized in terms of the unit impulse response. And in fact, in a certain sense, these, so it is the eigenvalues of this matrix which have a relevance, right? And I'm not bringing out the full connection because I might much better do that by looking at the original system. Indeed, let's now consider a situation where this, now by the way, this here of course when you have a finite length Hn, there is no problem of convergence. The discrete time Fourier transform would certainly converge. It's a finite length sequence, a finite summation, so it would definitely converge. Finite summation with each term having a finite magnitude, there's no problem. And in general, we don't know whether this would converge or not, but let's focus on a situation where the input, the impulse response and the output all have convergent discrete time Fourier transform. And now let's try and establish a relationship between them. So we say, so you see, yesterday we were talking about this whole idea of change of paradigm. So transform is a change of paradigm. It's a change of world view. It's not simply an operation in a sequence, it's a change of world view. What do we mean by that change of paradigm? So there we go. Let's take the discrete time Fourier transform of the input and the discrete time Fourier transform of the output, and let's try and see if they can be related. So you have this linear shift invariant system. With impulse response Hn. We have given to it the input x of n and we have produced the output y of n. And we want to ask what is the relation between the DTFT of x, h and y. And we wish to query the relation between them. Indeed, let us write down the DTFT of the output. So let's write an expression for the DTFT of the output. And let's expand the output in terms of the input and the impulse response. Now here we have a double summation. Again, and we find it convenient to make a change of variable. Right now the summation is on k and n. But now we'll use L to denote n minus k. So let's use L to denote n minus k. So we'll now work with the variables k and L instead of k and n. So for a particular k, if n runs over all the integers, so does L. Is that right? For a particular k, when n runs over all the integers, so does k. And therefore, we can rewrite this double summation as summation L going from minus to plus infinity, summation k going from minus to plus infinity, hk x of L e raised to the power minus j omega k plus L. And now we can decouple the two expressions. Do we recognize this? What is this? This is the discrete time Fourier transform of H. And it's independent of L. So it can be brought outside. Of course, remember that we are doing all this contingent to these summations converging. We assumed that in the beginning, but we're taking a situation where these summations converge. And in that case, what we have now is h e raised to the power j omega. Once you extract h e raised to the power j omega common, you get and what can do we recognize this? This is of course the discrete time Fourier transform of the input. Therefore, this is h e raised to the power j omega times capital X e raised to the power j omega. The DTFT of the impulse response this is a very important result. We are saying the discrete time Fourier transform, the output is the product of the discrete time Fourier transform of the input and the discrete time Fourier transform of the impulse response. Now we need to interpret what we really mean and we give it an interpretation. What is the physical interpretation? In fact, I would like you to reflect on it for a minute. Take just 1 minute and individually reflect upon what interpretation we can give this result. And then you may consult your partner for half a minute. Then we'll have volunteers. Yes. So, take 1 minute and reflect on what the interpretation will be, and consult your partner after 1 minute. Let's have everybody reflect for 1 minute. Try and reflect and see if you can come up with an interpretation. And after you reflect, then take half a minute to consult your partner. This time we'll just pass the mic around. Do we have volunteers to share something? You'd like to say something? Yeah. Or you can come here. Why don't you come here? Actually, you must also introduce yourself and then.
Hello, I'm Dr. Narendra Kumar Dasre. I hope this is a convolution theorem actually. My interpretation is this is a convolution theorem.
You're right. But that's what they say. Have you heard the story of the master and disciple? The disciple had a cup with him. The master wanted him to drink water. So the disciple was told, please fill the cup with water. And then the master told him, now pour more water into the cup. He kept on asking to pour water into the cup. So what happened? The water kept overflowing. After a while, the disciple wondered what's going on. Why is this person asking to go on pouring water into the cup when there's already a full cup there? Right? So then the master, that's what is happening. When you come with a full cup, then it's difficult to put anything into it. So, you're right, you're absolutely right, but your cup is full.
I'm sorry,
you can't
sir.
put anything into it. But can you give me an interpretation without knowing about convolution? I didn't use the word convolution. Use the mic.
I have the product of two sequences CHK and XK, HN and XN. Then we calculated here the DTFT. So I got actually the product of DTFT.
Yes. So what can you give it an interpretation? Can you interpret this? Yes, and yeah, good. Thank you. What you said is absolutely correct. Yes. Linear algebra is actually very simple and beautiful. As long as you come with an empty cup. Yes, come, yeah.
So we showed one result that when we take DTFT, then we are actually projecting on e raised to j.
Very
Now what happens to e raised to j omega n? That is just simply multiplier
yes.
coming out. So that multipliers are h of e raised to j, and that sequence is also projected. So
yes,
they multiply.
Yes, that's correct. So in a way, what you're saying is, if you look at the projection of the input upon e raised to power j omega n, the projection of the output upon e raised to the power j omega n is the projection of the impulse response upon e raised to the power j omega n multiplied by the projection of the input upon e raised to the power j omega. So, it really means that these e raised to the power j omega n work in a decoupled way. So, each of the e raised to the power j omega n's minds its own business, isn't it? As far as the component of the output along e raised to the power j omega n only requires you to know the component of e raised to the power j omega n in the input. It doesn't require. So, for example, let's take a concrete example. Suppose omega is equal to pi by 3. The component of the output along e raised to the power j pi by 3 n, angular frequency, normalized angular frequency pi by 3, only requires you to know the projection of the input along omega equal to pi by 3. It doesn't require you to know the projection of the input along omega equal to pi by 2. So, there's a decoupling of the different omega as far as the different angular frequencies. That means each of the angular frequencies works on its own when it goes to the system. Isn't it? You see, this is not very different from the following situation. Let's see. Yesterday, Professor Verma introduced you to the idea of a positive definite matrix, and he talked about the behavior of the eigenvalues and eigenvectors. So, you are aware that if you have a positive definite matrix A, and if it has let's say it's of dimension n cross n, so it would have n positive eigenvalues. Let's call them, say, lambda 1 to lambda n. And the corresponding eigenvectors, let's call them capital X1 to capital Xn. Now, these vectors also have a certain property. They are all orthogonal. Therefore, if you think about it, these vectors themselves form a basis. The eigenvectors of a symmetric positive definite symmetric matrix form a basis for n-dimensional space. So, if you took any vector, let's call it V. V can be expressed uniquely in terms of x1 to xn. So, let's call them summation k going from 1 to capital N, let's say Vk times capital X of k. Now, if you gave V as if you applied A to V, that means if you multiplied V by A, what would it be? It would be A times summation k going from 1 to n Vk xk. I'm sorry, that's correct, xk. Now, Vk is a constant, so that you can bring out. I'm sorry, rather you can take A inside. So, you can write Vk A times xk. But A times xk is lambda times xk. Is that right? So, what does it tell you? Now, AV, let's call this this is like the output, let's call it VO. Now, if you think of xk as a basis, xk going from 1 to n as a basis for the n-dimensional space, and this is an orthogonal base, not only is the basis an orthogonal basis for n-dimensional space. So, what are the orthogonal components of V0 in terms of this basis? What are the orthogonal components of V0 in terms of this basis? Yes, indeed, this isn't it, Vk times lambda k, obviously, because you have expanded them in terms of the xk, and it's unique, the expansion is unique. Therefore, so the components of the output in terms of the basis is a product of the component of the input and the component of the operator, the eigenvalue of the operator. So, now what you saw just now for the discrete time Fourier transform is a generalization of that, but it's a generalization on a continuous set of omega. Of course, is this getting pretty heavy? How many of you found this pretty heavy? Yes, I can see you were a little puzzled. Yeah, Yes. How many of you found this heavy? Raise your hands. Yes. Let's write. Would one of you like to come in and take half a minute and discuss this between yourself? I'd like one of you to come and explain to me in different words. So please, talk to you can straight away talk to one another. So talk to your partner and give me an try and interpret this. Come and share your interpretation. Take half a minute to 1 minute. And I'd like to hear some interpretation from you. You have interpretation? Yeah. Yeah, my question is, I've given you an interpretation which suddenly was pretty heavy. So I want you to come and explain the same interpretation. I want some volunteers. You can discuss it between yourselves and come and explain the same interpretation. Yes, do we have a volunteer? Yes, any volunteers to come and explain? Would you like to try now? Are you lighter anymore? No? Yes, any volunteer? Would you like to come? Well, yes. Okay, yes, you can come and try. Dr. Mukesh will again come and try. Let's take the example of Dr. Mukesh in terms of bravery. Yes.
In this expression, for a linear algebra, we map this vector to another vector domain by this linear map.
Yes.
In our DTFT, when we are taking the output DTFT, which is continuous in frequency, and it transform or change to another domain where the h of e raised to omega, x of e raised to omega. This is continuous its frequency. So it is a mapping from continuous to continuous. Continuous omega to continuous. Here the vector map into vectors.
Yeah, so here you have a discrete set. You have a discrete set of eigenvalues and coefficients of the expansion. So you've expanded any any vector v in n-dimensional space in terms of the eigenvectors of a positive definite symmetric matrix x of k, and you're saying that the output components are a product of the input component and the corresponding eigenvalue. That means there's a decoupled behavior of each of the eigenvectors. The eigenvectors allow you to decouple the output-input relationship. Okay? So, for that operator A, for that matrix A, the action upon each of the eigenvectors is decoupled. Projection of a vector, the output vector upon any of the eigenvectors is decoupled from the projection upon another eigenvector. So that operator, right? So thank you so much. That's right. So there's a decoupling effect here. There's a decoupling effect. So what you saw in n dimensions, in finite dimensions, has been generalized here to infinite dimension. Yes. 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 So you see, now let's go deeper into it. That's why I was looking for an interpretation from you. How would you obtain? Let's for example, yes. Oh, because omega is a continuous variable, isn't it? So what is the range of omega that we should take? We saw that yesterday, isn't it? What is the range? 0 to pi, that's correct. Omega only needs, in fact, actually no, omega needs to go from minus pi to pi, because it can be both ways. The rotation can be counterclockwise and clockwise, both. So omega needs to go from minus pi to pi. Is that right? Yes. 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 So for every point omega between minus pi and pi, the behavior is decoupled. So it only involves that particular omega. For the continuum, right from minus pi to pi. Yeah. That's right. Now, in fact, let's go further. Let's go deeper. Let's look at this. How would you, now you see, eigenvectors are unique only up to a constant, isn't it? So you can always normalize the eigenvector. You can always make it unit norm. What does it mean? you can make the magnitude equal to 1. So you can all, without loss of generality, you can always say the norm, that is, the norm, the 2 norm of this is equal to 1. Is that right? That means if you take the sum square of the components of the eigenvector, you can insist that they become 1, and you can do that by multiplying it by a constant. Right? You can always normalize. You can always take an ortho. So not only will you get an orthogonal basis, you can also make it an orthonormal basis. There's no problem, right? Now suppose, so without loss of generality, let's assume that x1 to xk is an orthonormal basis. For n-dimensional space. In that case, how would I obtain the vk? Suppose I have the vector v. How will I obtain the vk? If it's an orthonormal basis, how will I obtain the vk? Yes? Yes? Yes, yeah, something, yes. The inner product, of course. So what is vk then? Vk is the inner product of v with xk, of course. Is that right? So vk is the inner product of x with v with xk. What is the geometrical interpretation? You take a dot product of the vector with a unit vector in the direction in which you want to project. Is that right? So if you have an n-dimensional orthonormal basis, you can find out the projection along each of the directions by taking an inner product. So vk is an inner product of v with xk. Similarly, you could find out the v to vo again. You could take the inner product. So what are we really saying? We are saying inner product of the output with xk is equal to lambda k times, isn't it? That's what we are saying. If you take component wise for each k, this is the relationship that you have. And this is now being generalized to the discrete time Fourier transform. See that? Now you have a continuum. You have a continuum of eigenvectors and eigenvalues. Right? Now, you see, this is a very beautiful thing. What it says is that there's a decoupling. In fact, for those of you, I believe that there's also a more general theory for this called the spectral, spectral theory of operators. So I think one example of the spectral, before I understand, I'm told that there's a whole general field of spectral operators, spectral theory. So this is one kind of spectrum. But anyway, notwithstanding that, therefore, this is very interesting. So if you can decompose the input into its components along different rotating complex numbers, you can find out the output component wise. And now we have to see, suppose you know all the components. So can we reconstruct? This is a question that we need to answer to complete our discussion. Can we reconstruct xn from capital X e raised to the power j omega? So we have seen the other way, that is, we know how to calculate. We have given an interpretation. X e raised to the power j omega n, x e raised to the power j omega is first inner product of xn with e raised to the power j omega n. Isn't it? That interpretation we know. But now we want it the other way. Suppose you know all these inner products. So suppose we know x e raised to the power from minus pi to pi. Then can you reconstruct? You see, in principle it should be possible. Well, in principle it should be possible if you have not lost something. If you have projected xn along all these different omegas, whether or not the answer to this is yes will depend on whether you have lost something in all these projections. If you have lost nothing, if everything that was there in xn is indirectly present in all these projections, then you should be able to reconstruct. Now here I am again going to give you an opportunity to think and come up with an answer. Again, now take recourse to your high school vector geometry and tell me if you can come up with an answer to this question. Can we reconstruct? How would we reconstruct xn from capital X e raised to the power j omega, omega going from minus pi to pi? Again, I give you a hint. Go back to high school geometry. Can you, if you, just like you interpreted calculation of x e raised to the power j omega in terms of high school geometry, that's like a dot product. Now, you're asking, can you reconstruct a vector from its dot product? Right? In fact, you almost have an answer, but I'll give you half a minute. So take half a minute, think on your own, then take half a minute, discuss with your friend, and then after 1 minute, we'll have volunteers. First, take half a minute and think on your own, and then take half a minute to discuss with your friend. The question is, can I go the other way? So I've gone from xn to x e raised to the power j omega. Can I go back to xn from x e raised to the power j omega? So if I know the x e raised to the power j omega, for omega going from minus pi to pi, can I reconstruct xn? Can I reconstruct xn from its components along different domains? I gave you a hint, use high school geometry in some sense. Or high school vector algebra. Well, we are nearing the end of 1 minute. Do we have any volunteers? Do we have volunteer? Maybe I'll definitely have volunteers if I now give you an even bigger hint. Let's take a two-dimensional vector. And you have two unit vectors, u1 and u2, u1 cap and u2 cap. So I've given you these. How will I reconstruct B from these two inner products? Now I've given you the answer almost. Yes, yes. Of course. So I would reconstruct B as B u1 times plus, isn't it? Yeah, so simple. I've almost given you an answer. Now I give you another half minute. Yes. Now I'm sure I have volunteers to answer my bigger question. Ready? Ready with an answer? Yes. That's, but in some sense you do know the dimension. In some sense. Again, as I said, little not so rigorous, but still. How many omega, or I won't say how many is not the right way, but is there a range of omega in which you must work? Yes? Minus pi to pi, that's correct. In that sense, you know which omega you need. Is that right? I can see a smile on some faces. Are you ready with an answer? Yes, you're ready with an answer? So do we have volunteers? Yeah. Anybody would like to help me with an expression? How? Yeah, any volunteers? No? Yes? Yeah, may I have any volunteers to come and write an answer? You want to do it? Yeah. So bring your notes along. Nice.
We know x of e raised to j omega is such kind of projection or inner product, and with respect to that c omega, so we need to take the same rotating
Yes,
vector
that's correct.
is e raised to j omega, and now omega ranges from minus pi to pi, which is continuous. So instead of taking additions of all, maintaining continuity, take integration, and
You would need to replace an addition by an integral.
so that will be
Okay, now these are places where we are not being very rigorous. It's not a very rigorous. It's an intuitive argument. It's not very rigorous. It's not incorrect, but it's not rigorous. Yeah, it doesn't matter.
this and this range
Yes.
normalize.
Yeah, and now here, now what is the catch? You see, e raised to the power j omega. Now, what was the, see, these were orthogonal, but it's not enough for them to be orthogonal. They needed to be orthonormal. They also need to be unit norm. That means that you might need to put a constant there to normalize. Some constant. We don't know what that constant. Put some constant, k. And we'll find that k out.
By plugging it again in.
Yes, so very good. That's correct. Thank you. Very good. So do you see what he's saying? He's saying multiply each component by an orthogonal. So now you see he's observed that these e raised to the power j omega n are like orthogonal components for different omegas. And you're multiplying by the corresponding orthogonal component, you're integrating over them, but you need to also allow a constant to be there. Strictly speaking, this constant might need to depend on omega. So actually the constant needs to be inside. But let's see, again here we are, doing, as you say, if you can, then why not? Let's see if you can keep the constant independent of omega and still get a reconstruction. How would you get a reconstruction? If you evaluated this and you were able to find a k for which this gives you back xn. Let us see if we can do that. So let's substitute for x e raised to the power j omega. Let's examine integral minus pi to pi x e raised to the power j omega times e raised to the power j omega n. This can be written as minus pi to pi integral summation k going from minus to plus infinity x of k e raised to the power minus j omega k times e raised to the power j omega n. And this is summation minus pi to pi. Now here, let's interchange the order. So let's take the summation outside and take the integral inside, because the integral is on omega, this is independent of omega. So I could take, of course, now by the way, this is where a little bit of rigor strictly is required. This kind of an interchange requires certain conditions. But let's assume that those conditions are not very, they're not very demanding. So in most reasonable situations, these conditions allow the interchange. So we have this. Now this is an easy exercise. All of you please evaluate this. Evaluate this integral. That's not at all difficult to evaluate. Of course, you will need to do it for two different cases. How many of you have an answer? Will you raise your hands? For the integral, I'm saying. Yeah, you have a value? Yes. Could you come and share your value? Bring your notebook along. I want you to give me a, a different. Yes? Yeah, come, Kunix. I think that's, you can come and share your answer. Pardon? Doesn't matter. If you're not sure, then it's all the more reason to come. Use the mic.
The summation. Actually, this integral part, if we do separately, then it is e raised to j omega n minus k divided by n minus k
J into n.
j into n minus k. If n is not n minus k not equal to 0.
That's
If n minus k is 0,
yes.
then this becomes 1.
Yes.
And so that value is 2 pi.
That's correct.
And if we evaluate this value from minus pi to pi,
Yes.
it is 0.
Yes, because you take the same value at the two extremes. Minus
So
1 to the power n minus 3.
This summation holds only for if k is same as n.
That is
And in
correct.
that
For
case,
all
this is
other,
2 pi.
so only at one value of k, namely n, will that integral be non-zero. That is right. Yes, correct. Absolutely correct. Thank you. How many of you get this? You raise your hand. You got it? Yeah. How many of you don't understand this? Have we understood it now? Yes, have we understood this? Therefore, you get xn times 2 pi. So now do we have k sitting staring at us in the face? Does k come out clearly from here? K must be 1 upon 2 pi. So you need to multiply by 1 upon 2 pi to take care of this factor of 2 pi. Therefore, now we have an expression for the inverse discrete Fourier transform. That is, x of n for every n is 1 by 2 pi integral minus pi to pi x e raised to the power j omega e raised to the power j omega n d omega. So, you see, what does it mean? If you wish to calculate the output of a linear shift invariant system given the input, there are two ways of doing it. You can do it directly in time by evaluating the expression that you saw, summation hk, xn minus k and so on, or you could do it component wise. You could decompose the input along the different e raised to the power j omega n's, evaluate the output for each of the components and reconstruct the output from its components. Now, let's take a case of a finite dimensional situation. Let's take a case where your input has a finite number of samples and the output also has therefore finite number of samples, provided the impulse response also is of finite length. Actually, that's not necessary. Well, no, actually it is. You can't input the impulse. One of them is of infinite length. You are not guaranteed the output is of finite length. So let's take the following situation. Suppose xn has, say, only capital N samples. Hn has L samples. So, as an example, in yesterday's, for the system that we saw yesterday, what is the value of L? 2, that's correct. So, the example, for the system that we saw yesterday, L has the value 2. So, if x and both of them are integers, so it has n samples, Hn has L samples. How many samples would Yn have? How many samples? Please think and tell me. Take a minute to think and tell me. How many samples would Yn have? Yes, yeah. You can, if you like, could work it out on your, it would be recommended you work it out on your notebook. Yes, yes, yes. N plus 1. N plus, for L equal to, so in general, for N and L in general. That is correct. Yes. Would you like to come and justify what you said? Yes. That's correct. Anybody who would like to justify, he's correct. Gupta says it should be N plus L minus 1. So, yeah, he wants to only justify it. Yes.
For x of k, having a non-zero L value.
That is right. Contiguous. Maybe contiguous L values, yeah.
So, when we are putting different values of n, we are getting only non-zero this or because x of k means we are having n number of non-zero.
That's right.
And we are shifting
Yes,
y of n using n plus l minus 1 non-zero.
very correct. Yeah, that's a good way of. In fact, there's a good way also to see it. Thank you. Thank you. Now, there's a good way of seeing this by what I call the train platform analogy. So, if I were to put HK on a platform, let's, without loss of generality, let the non-zero values be from 0 to L minus 1. And let X come as a train, right? So, let you have X, you have X0, X1 coming like this as a train up to X of n minus 1. Now, when X0 is here, you get Y of 0. When X0 moves here, X0 is multiplied by H1 and X1 is multiplied by H3. So, I'm sorry, this should be, yeah, I think that's okay. So, sorry, it should be, well, yeah. So, well, so, see, the thing is, so let's write down the expression, let's write this expression down. So, Y of n is summation k going from 0 to L minus 1, h k x of n minus 1. So, see, so you should think of hk is the static part and you have x of n minus k moving along. Is that right? Now, the sequence x, you could visualize the sequence x moving along this to generate, and keep stopping at every point, it generates one point. Isn't it? So, when x of n is here, it generates y of n, right? Y of 0. When x of n comes here, it generates 1, and so on and so forth. So, up to what point will this train and will the passengers on the platform interact with the passengers on the train? Up to a point where the last bogie of the train reaches here. And when will the last, so that means what is the total length which is required? L minus 1 here plus n. I'm sorry, L from 0, yeah. So L plus n minus 1. Whatever way you want to do it. So L plus n minus 1. When you go n minus 1 steps here, the last passenger here interacts with the last passenger in the train. After that, this train moves away. There is no interaction at all. That's another way of understanding. Therefore, you get n plus L minus 1 samples in the output. Now, you could think of a situation where the input can also be thought of as having n plus L minus. So, really that means if you want to find out the output, you need to work in an n plus L minus 1 dimensional space, because it has only n plus L minus 1 dimension. The output has only n plus L minus 1 sample. So, it's an n plus L minus 1 dimensional vector, isn't it? And the input is an n-dimensional vector, the impulse response is an L-dimensional vector. But an n-dimensional vector can always be embedded in n plus L minus 1 dimensional space by making all the other components 0. So, here the output is an n plus L minus 1 dimensional vector, the input is an n-dimensional vector, and the impulse response an L-dimensional vector. But an n-dimensional vector can always be embedded in n plus L minus 1 dimensional space, and so can be impulse response. So, you could think of it as an interaction between two n plus L minus 1 dimensional vectors to produce a third one, right? And if you require only n plus L minus 1 dimensions, you don't need all of those omega. You can choose any n plus L minus 1 distinct omega. And that is the idea behind what you call the discrete Fourier transform. So, we saw the discrete time Fourier transform, but the discrete Fourier transform discretizes the frequency as well. So, you can take only n plus L minus 1 discrete values of the frequency, and you can use those to get an input-output relationship. That's what the idea behind discrete Fourier transform. But unfortunately, we will have to conclude the lecture here as far as this topic goes. Yes. Let's hope there is another opportunity to learn more. I'm sure many of you will pick up many more things having been ignited with